Okay, so welcome back to this next video in which we are discussing the serotonin receptors. Okay, so we're currently in the process of discussing the many different types of heterotrimeric G proteins. So we're currently looking at the diversity of alpha subunits, and we've discussed that there are 16 different genes for alpha subunits and 21 different subunits. Okay, so we're now going to have a look at the 16 different genes for alpha subunits. Now, they are categorized into families. Okay, so the first family of G-alpha subunits is the G-alpha S family. Okay, like so. And this contains two genes. It contains the G-alpha S gene, okay, and all alpha subunits of heterotrimeric G proteins are named in this way with a capital G and then the subscript denoting which of the three subunits we're talking about, and then you subscript that subscript with the actual specific subunit you're talking about. Okay, so this is the G-alpha S alpha subunit of a heterotrimeric G protein, and then there is another gene for an alpha subunit that's also in that family, and it's then the G-alpha OLF gene. Okay, right, so those are the two alpha subunits of heterotrimeric G proteins which are put in this G-alpha S family of alpha subunits. Okay, and both of those, when activated, will have similar actions, i.e. they will target adenylyl cyclase enzymes. Okay, then we have the G-alpha I/0 family of alpha subunits of heterotrimeric G proteins. Now this contains 8 different alpha subunits of heterotrimeric G proteins. Okay, so it contains G-alpha I1. Okay, that's the first gene. Then there is G-alpha I2. There's also G-alpha I3. Okay, and then continuing on, we also have G-alpha 0. Okay, we then have G-alpha T1 and G-alpha T2. Now let me tell you about G-alpha T1 and G-alpha T2. So basically, in the pathway downstream of the G protein-coupled receptor rhodopsin in the eye, you have the activation of a heterotrimeric G protein. Okay, so once that G protein-coupled receptor has been hit by light, it will then interact with heterotrimeric G proteins, and the alpha subunit of these heterotrimeric G proteins will either be G-alpha T1 if we're talking about a rod cell, and it will be G-alpha T2 if you're talking about a cone cell. Okay, now the heterotrimeric G protein which the light-activated G protein-coupled receptor interacts with is called transducin. Okay, so these two G-alpha T1 and G-alpha T2 alpha subunits, those are the alpha subunits within transducin heterotrimeric G proteins. And G-alpha T1 is the alpha subunit within rod transducin, and G-alpha T2 is in cone transducin. Right, then after that you also have the G-alpha Z alpha subunit, and also G-alpha GUST, which is involved in gustatory transduction. Okay, right, so that's the 8 different genes for alpha subunits of heterotrimeric G proteins that are all put into this G-alpha I/0 family of alpha subunits. Okay, right. One thing I would just like to mention, because you'll see this a lot if you read papers, okay, G-alpha 0 has 2 splice variants, and the notation for these splice variants is quite nice, so I'll give you the 2 splice variants of G-alpha 0. Okay, so the 2 splice variants of the G-alpha 0 gene are called G-alpha 0A and then also G-alpha 0B. Okay, so they're not 2 separate genes, they are 2 separate splice variants of the same gene. Okay, right, so that's 8 members within the G-alpha I/0 family. Then let's move on to the G-alpha Q/11 family. Okay, so this now contains 4 alpha subunits of heterotrimeric G proteins. So in the G-alpha Q/11 we have G-alpha Q itself, then we also have G-alpha 11, then we have G-alpha 14, And then finally, we also have an alpha subunit known as G-alpha 15/16. Okay, now the reason this alpha subunit is called G-alpha 15/16 is because in mice, this alpha subunit was called G-alpha 15, and then in humans, the people who worked in humans called it G-alpha 16, and then later it transpired that these two were actually analogous, so we decided that G-alpha 15 was just the mouse equivalent of G-alpha 16 in humans. Okay, so there is now a movement to have both of them renamed G-alpha 15/16, and then it goes for mice and humans, basically. Okay, so that's why it's called G-alpha 15/16. Don't think that that's two separate subunits, though. There is one gene for that. Okay, then the final family of alpha subunits of heterotrimeric G proteins is the G-alpha 12/13 family, which contains G-alpha 12 and then also G-alpha 13. So that now is the 16 different genes for alpha subunits of heterotrimeric G proteins. Here we have 2. Then 8, that takes us up to 10, then 4, that takes us up to 14, 2 more, that's 16. So these are the 16 different genes for alpha subunits, and some of them have multiple splice variants. For instance, G-alpha S has a large number of splice variants, which is how you go from 16 genes to having 21 different alpha subunits. So if you are building a heterotrimeric G protein, there is a huge scope for how many different alpha subunits you have to pick from, basically. Okay, and these alpha subunits have been classified into these families like so, because all of the members within a certain family will have certain functions, okay? So later when we discuss the G protein cycle, we'll see what happens is the alpha subunit, when it gets GTP put on it, splits off from the beta gamma subunit, and both of them then go off to have downstream targets. Now, the alpha subunits in G-alpha S tend to activate adenylyl cyclases and therefore raise cyclic AMP. Meanwhile, the alpha subunits in this G-alpha I/0 family, they tend to decrease cyclic AMP level. Okay, so they inhibit adenylyl cyclases. G-alpha Q/11, these tend to activate the phospholipase C beta pathway, leading to the release of calcium from the ER. And finally, G-alpha 12/13, these tend to activate remodeling of the cytoskeleton. So we group the alpha subunits according to what they do, basically. Okay, so those are all the different types of alpha subunits then. Let's now move on to the different types of beta subunit and the different types of gamma subunits, so that we've got a complete picture of how many different alpha subunits there are, how many different beta subunits there are, and how many different gamma subunits there are. Okay, right. So let's now move on to the beta subunits then. So we have 5 genes for beta subunits. Okay, so there are 5 genes, but then again there are 6 different subunits. So we have 1 gene that has 2 splice variants, basically. Okay, so I'll start with the 5 different genes. You have G-beta1, G-beta2, and these are really nicely named. G-beta3. Okay, so G stands for heterotrimeric G protein. Then you have to label which sort of subunit you're talking about. So we're talking about beta subunits, and then you subscript it with its number. G-beta4, and then finally G-beta5 down here. Okay, now G-beta1, G-beta2, G-beta3, and G-beta4, they all have only 1 splice variant, okay? So they create the G-beta1 subunit, the G-beta2 subunit, the G-beta3 subunit, and the G-beta4 subunit. G-beta5, however, has 2 splice variants, and these are called G-beta5-5, okay, and also G-beta5L. Okay, so there are these 2 different splice variants of the G-beta5 gene, basically. Okay, so that overall gives us 6 different beta subunits of heterotrimeric G proteins. Finally, let's talk about gamma subunits. For gamma subunits, there are 12 known genes for gamma subunits of heterotrimeric G proteins, and these code for 12 different subunits. So this one's nice and simple. There are no silly splice variants. Okay, so the naming is almost perfect, but it has one little blip, so let me talk you through this. So there is G gamma 1, there is G gamma 2, there is G gamma 3, there is G gamma 4, there is G gamma 5, then there is no G gamma 6, and we go straight on to G gamma 7, then we've got G gamma 8, G gamma 9, and then it goes all the way up to 13. Now I might as well finish it because I've got this far. G gamma 10, whoops, missed off the G, I'll have to put it up here. Okay, there we go. G gamma 11, G gamma 12, and then finally G gamma 13, which gives us 13 different genes, and all of these code for just one protein as far as we know, and that gives us 12 different subunits for the gamma subunit. Okay, so when building a heterotrimeric G protein, there is an enormous great scope for producing many different heterotrimeric G proteins. There are 21 different alpha subunits you have to choose from, 6 different beta subunits, and 12 different gamma subunits. Now I'd like to just say a little few words about how you name the different heterotrimeric G proteins. So strictly speaking, what you should do when you name the heterotrimeric G proteins is it would be very nice if you named exactly which alpha subunit, exactly which beta subunit, and exactly which gamma subunit you have. Okay, so an example would be G alpha I1, beta 1, gamma 1. This would tell us exactly which alpha subunit you have, which beta subunit you have, and which gamma subunit you have. However, people very, very rarely know exactly which alpha subunit, exactly which beta subunit, and exactly which gamma subunit they have. So often people will just label heterotrimeric G proteins with which alpha subunit they know they have. Okay, so you might call this GI1, for instance. Now, some people don't even know exactly which alpha subunit they have. For instance, the alpha I1, the alpha I2, and the alpha I3, which remember are all in this family, they all pretty much have very similar properties. Okay, so often people find it difficult to distinguish between which one they're talking about here. So people would just write GI for a heterotrimeric G protein, which has an alpha I subunit within it. Okay, and they wouldn't tell you exactly which one of the alpha I's it was. Okay, sometimes people don't even know exactly which member it is in the family, so instead they'll just subscript the heterotrimeric G protein with which family the alpha subunit is in. So for instance, someone might call this a GI/0 heterotrimeric G protein, and all that tells you is that the alpha subunit is somewhere within the family of G alpha I0 alpha subunits, basically. Okay, right, so that's just a little word on the naming of heterotrimeric G proteins. Okay, right, so let's now go back to the G protein cycle then. Okay, now I think I'll draw things out new. Okay, so we've got our G protein coupled receptor here now. And what's happened is the ligand has come along and bound to the G protein coupled receptor. And now let's say our G protein coupled receptors are a rhodopsin family G protein coupled receptor, since all of the ones we're interested in, which are the serotonin receptors, all of those are rhodopsin family G protein coupled receptors. So they bind their ligand within the transmembrane domain. What happens when the ligand binds is you get a conformational change in the intracellular loops, basically. Okay, so what's going to happen is the intracellular loops will move, and they'll create a binding domain for the alpha subunit of a heterotrimeric G protein. Okay, now most G protein coupled receptors will be specific for a certain alpha subunit, i.e. they don't just bind to any old alpha subunit, they will be specific for a certain one, or at least a certain type. Okay, so for instance, they might bind any of the alpha I's, basically, maybe alpha I1, alpha I2, or alpha I3. Okay, so let me draw this now. So what's going to happen is our alpha subunit is going to come and bind to the intracellular loops of the G protein coupled receptor. Now to show this, what I'm going to do is I'm going to spin the G protein coupled receptor around so that I don't have this carboxylic acid domain in the way. So I'm just rotating it 180 degrees, but I'm not actually changing it. Okay, this is just for the purposes of the picture. So here's the amino terminus now, and here is the carboxylic acid terminus. Okay, and we have our ligand bound here. What's going to happen now is here along comes our alpha subunit, and this is going to bind to the intracellular loops of our heterotrimeric G protein. Now, importantly, the alpha subunit can only bind to the intracellular loops of the heterotrimeric G protein if it's also got a beta-gamma subunit bound to it. Okay, without the beta-gamma subunit here, it can't bind. Okay, so only alpha subunits which have a beta-gamma complex bound to them, i.e. only alpha subunits which are in the off state, can bind to the intracellular aspect of our G protein coupled receptor. So let's colour this in here. So let's colour in our alpha subunit in red here. Okay, like so. Then let's colour in our beta subunit in blue and our gamma subunit in green. Okay, so the beta-gamma subunit doesn't itself bind to the intracellular loops, but it is necessary that it is bound to the alpha subunit in order for the alpha subunit to bind to the intracellular loops. And these two lines here, those are just the lipid moieties that are anchoring the two portions of the heterotrimeric G protein, the alpha subunit and the beta-gamma complex, into the inner leaflet of the phospholipid bilayer. Okay, right. So now what's going to happen is when the alpha subunit binds to the intracellular aspect of the G protein coupled receptor, what will happen is the GDP will fall out of the alpha subunit, and then a GTP molecule, the guanosine triphosphate molecule, is going to come in. Okay, when the GTP comes in, what happens is the beta-gamma complex can no longer bind to the alpha subunit, so it falls off basically and goes off in the cell membrane. Okay, when the alpha subunit no longer has the beta-gamma complex bound, it can no longer bind to the intracellular aspect of the G protein coupled receptor, so it also detaches from the G protein coupled receptor and will also go off into the membrane. So let's now draw this. So what we have is a free alpha subunit that's in the membrane that has its GTP bound to it, and this will go off and interact with targets basically. So this is an alpha subunit in the on state. And then we also have our beta-gamma complex over here, which again is off on its own now. It isn't associated with the alpha subunit. So here is our alpha subunit. Okay, so let's once again colour it in. So here is our alpha subunit in red here. Okay. In blue, here is the beta subunit. And then in green, here's the gamma subunit. Okay, and both of these signaling molecules will now go off and interact with targets. Okay, so let's say here is a target for the alpha subunit of the heterotrimeric G protein. Okay, and we'll call this target 1. And of course these targets will either need to be integral membrane proteins, or they'll need to be attached to the inner leaflet of the phospholipid bilayer in some way, because our alpha subunit and our beta-gamma complex are within, well not within, but attached to the inner leaflet of the phospholipid bilayer. Okay, now, as I said earlier, the target of the alpha subunit will depend on which alpha subunit it is. So for instance, the alpha subunits in the G-alpha S family tend to go and bind to adenylyl cyclase enzymes and activate them. The alpha subunits in the GI/0 family tend to bind to adenylyl cyclase and inhibit it. The alpha subunits in the G-alpha Q/11 family tend to bind to phospholipase C-beta and activate it, and G-alpha 12/13 activates all sorts of pathways to cause cytoskeletal remodeling. Okay, right. So the specificity of the different beta-gamma complexes for different targets isn't well understood at all. At the moment, it seems to be that the beta-gamma complex it's horrendously naive, but we think that it just does the same thing, basically, not depending on which beta or gamma subunit you have. That's almost certainly over-naive, though. Okay, right, so this also interacts with targets is the important message there. Okay, right, so when the alpha subunit binds to its target, what will happen is not only does the alpha subunit cause some change in the target, but also the target causes a change in the alpha subunit. The alpha subunit is actually an enzyme. It is capable of breaking GTP down into GDP and inorganic phosphate. Okay, so the alpha subunit is actually a GTPase. It's capable of hydrolyzing GTP down to GDP and inorganic phosphate. And basically, when it binds to its target, the target will activate this GTPase activity, and then it will hydrolyze the GTP to GDP and inorganic phosphate. The inorganic phosphate will be released, and the GDP will remain bound to the alpha subunit. So the alpha subunit will turn itself off, basically. So it's only activated for a little bit of time, and then it turns itself off. And when it turns itself off, it detaches from its target and will go and find a beta-gamma complex again, take the beta-gamma complex from the target that it's bound to, and then rebind together to make the inactive heterotrimeric G protein. So basically, this is why this entire process is called a cycle, because we're back to square one now, where we have the inactive heterotrimeric G protein once again. Here's the alpha subunit with guanosine diphosphate bound to it, and it's taken the beta-gamma complex away from its target so that the beta-gamma complex can be with the alpha subunit again. Okay, right. So that's why it's called a G protein cycle, because it goes round and round and round, and when the G protein coupled receptor becomes activated again with its ligand, you will go on another cycle, basically. Okay, right, so we'll call it there for this video, and in the next video what we'll discuss is firstly what the different serotonin receptors actually interact with, i.e. which heterotrimeric G proteins or which alpha subunits do the heterotrimeric G proteins, which the different families of serotonin receptors interact with. Okay, and then we'll also discuss the 5-HT3 family of serotonin receptors.